And then you want to do this Master of Physics of Complex Systems at the Theatre de Toulouse in Paris. Make you realize the best place to do physics of complex systems is here at IFISC. Today we will talk about a very important topic, in which important people are involved.
So yeah, we'll talk about coevolution. Talk about a couple of things which are not strictly speaking coevolution, but are related to the model that I've been using. Well, this work, of course, has been done with my co-workers and, and also Federico. That I think you all know.
No, too many young people. They don't know.
He's in here, isn't he? So let's say that I will start basically from what Juan said in his PhD defense thesis. In his thesis, motivating the use of linked states. I will give a general context about the uses, the different uses of linked states in different dynamics, in different articles. I will introduce a little bit the model that Juan used, and which is basically, or more or less, is the same that I use by adding different things. So in a first step, I will add noise, so in the form of a temperature. So I will go from the majority rule that Juan studied to a complete Glauber dynamics. As we will see, majority rule is basically a zero temperature Glauber dynamics. There, I will start the robustness of the trapped configurations that Juan detected. We will see that some of those configurations appear to be quite robust to temperature, to slight temperatures, to small temperatures. And then we will see what happens when we introduce coevolution. So when we introduce a network which evolves in time with the states of the links. There we will see that the states, the configurations that before with temperature were robust, now they are broken, so they order all of them. But we find a fragmentation transition, so the system can be found in one component, one whole component ordered, or in two components basically. And then I will draw some conclusions and give an outlook of different coevolutional things that we are starting to do now. So let's start with the motivation. It's clear that traditional models of social dynamics have always focused on properties of the nodes. No? So, for example, an opinion about something can be a property of the node. A disease can be a property of the node. We have different models, like the voter model, voters like Abrams-Strogatz for languages. We have spreading models for diseases, for gossip, information, whatever. However, in some cases, the variable of interest is not a variable of the nodes, not a variable of the agents, but a property of the interaction. So, for example, recommended and rating systems, when you rate a book, for example, it's not a property of you, it's not a property of the book, it's a property, let's say, of the relation, of your relationship to the book. So you give 4 stars to this book, or you give 2 stars to this other book. But other user can give different ratings to the same book. Also trust, friendship, enmity. You can be friends or enemy with somebody. You can have different levels of trust. For example, in this graph, trust is related to, let's say, 2 amounts of emails interchanged by 2 people. So it is a state of the link. And they use this, in particular this graph is from a company which uses these trust networks to filter spam, basically. The problem with the previous examples is that this is bipartite network, so quite difficult to treat. This is directed network, again, difficulties which are not needed. So what we use is a prototypical example, which is a competition of 2 languages which have the same prestige in a society. So it seems obvious that language is a property of a relationship. It's not a property of English, it's not a property of me, it's not a property of you. Maybe the knowledge of English is a property of you and me, but the language in which the interaction takes place is a property of the interaction. We can have the same interaction in Spanish with most of you, for example. So when one treats language as a property of the link, you have something very interesting, which is that bilingual speakers appear in a quite natural way. Because obviously you can have different links with different people in different languages, in different states, basically. So a competition of two languages is basically a link dynamics. This is taken from, this is an idea which was already introduced in the end, not developed, but in the end of the PhD thesis of Xavi Castelló. They already introduced this idea of treating the competition of two languages as a problem of link states, not of node states. So if we go now to the literature on link states, we will see that link states were actually introduced quite early in the literature. They were introduced, for example, well, as a first example, by Heidegger's social balance theory. Social balance theory, you know, these triads where you are friend of your friend's friend or something like that, no? Or enemy, you have triads.
What?
In relationships between three people, there are balanced and unbalanced triads, no? So, for example, this is unbalanced because you are not going to be friend of the friend of your enemy. No? This is unbalanced too because you are probably going to be friend of the enemy of your enemy. Yeah, that's why. Yeah, that's why. That's why some of them are. They call it balanced or unbalanced, but it's basically stability. Let's say. The problem with this, well, the reason why we don't treat this and we prefer focusing on languages is that here the states are not equivalent. So all positive or all negative are not equivalent. This one is balanced and this one is unbalanced. From 1946, of the first introduction of Heidegger's social balance theory, we have a lot of articles, and especially recently there are some articles by Redner and also Daniele Villone and so on, where they treat this problem in different manners and they do some analytical treatment of it. Also, it's important that recently we are beginning to have a lot of data, like big data, regarding this relationship. No? We have online games where there are friendship enmity relationships. So we can extract the data, and basically there are several papers studying if this is more or less like this. No? If those unbalanced triads are less represented in the data. In this article, for example, they find that yes, those triads are more represented than the other ones. There are also two more recent examples. One is community detection, where if you, instead of assigning states to the nodes and then trying to detect communities, you assign colors, let's say, to the links, and then you try to detect communities. The good thing about this is, again, the same as in the example of languages, that in the example of languages you can have bilingual speakers. In this community detection problem, you have overlapping communities. So you have nodes which can be part of two different communities, for example. And a quite recent example, last year, or 2 years ago, network controllability. So sometimes in some kind of networks, like internet or some communications networks, the important thing is to control the state of the links, not of the nodes. So it's just one example of it. But let's focus now on the link states majority rule that Juan used, and which is the basis of what we are going to do next. What we have here is a network composed of n nodes and n links, fixed number of nodes, fixed number of links. the states are defined on the links, and the states are they have two options. So you can be +1 - 1, language A, language B. You can be straight line, dashed line. And the dynamics they use in this article, for example, is a majority rule. What is it, a majority rule? First, the basic algorithm is states of the links are distributed randomly. Then we randomly choose one link and we update it according to the state of the majority. So if in this example you have 1, 2, 3, 4, 5 neighbors in a straight line and only 3 in dashed line. So when you update this link in the middle, it will go to the straight state. It's quite simple. Here the question they asked is, this system, does it order for different topologies? So if I do this with different topologies in a fully connected network, in a random network, does it order or not? And what they find, and this is quite well explained both in the defense of Juan and in his thesis, what they find, let's focus on Erdos-Renyi networks because those are the ones that I will going to use. What they find is that as opposed to node dynamics, consensual states are underrepresented. In fact, if the network is from 1,000 nodes, for example, it's almost impossible to find one consensual state. What they find is frozen coexistence and dynamical coexistence. So the final state of the network, those are basically absorbing states, where you find the network with links in one state and links in the other. But those configurations are frozen, so they cannot change, or they are dynamical traps based on linked states. A dynamical trap is, for example, this, where you have the same, where a link has the same number of neighboring links in one state and in the other. So the probability of change is 1/2, and it keeps changing, blinking forever. A frozen trap, we have an example here, where you have a cluster of nodes in one state, separated by one link from a cluster of links in the other state. So this link, since you have here more neighbors in the straight state than here in the dashed state, this link is frozen in the straight state. Okay? Here you see the difference. I mean, what they show in the article is basically that it is not trivial to run the dynamics on the links or on the nodes. There is a big difference because in the nodes, when you run the dynamics in the nodes, most of the times you find consensus. You only find frozen and dynamical coexistence in 0.02% of the realizations. While if you run the dynamics on the links, you basically always find frozen and dynamical coexistence. The explanation they give for this is that, in fact, well, one of the explanations or qualitative explanation is that when you run a dynamics on the links, what you're basically doing is running a dynamics on the nodes of the line graph. The line graph is basically a graph where a network where the nodes represent the links of the original graph. So if two links are connected through a node in the original graph, then they will have a link connecting them on the line graph. It's a little bit tricky, but so more or less you have an idea of it.
At the end, what you are doing when you study the links dynamics is changing the
topology.
The topology of the network. So,
yeah, basically.
I mean, if you know how the topology changes, you don't have to study the links dynamics. No? I mean, if you know how to map from one network to the
other one, when you can do it, yes, of course. It's the same. You're just changing from one topology to another. But the problem is that in most of the cases, this change of topology is precisely what is relevant. Because as you saw previously, you can say, yeah, but come on, node dynamics and link dynamics is more or less the same, you just change topology, but as you see, the result is totally opposite. So you are right, you can always go to the line graph, but precisely maybe it's that change of topology which is important.
Yeah, but what was not clear for me was, why it is interesting to study the link dynamics if once you know the change in the topology, you know what happens. What is already happening.
But then you can have different things, because you can also have what I will show in the end is basically adding another dynamics on the node or adding a rewiring, because then you have.
You can combine both.
There are things that you do on links that you cannot do in the line graph, let's say. So you can define dynamics which are only which you cannot map to nodes, let's say. But in this case, yeah, it's changing in topology.
I don't know if you're going to speak later on, but what properties of the network are preserved when you go to the line graph, if any?
There are some properties preserved. What you do when you go to the line graph, the most relevant change is that you create a community structure. Because, as you see here, each node of the original graph becomes a fully connected click in the line graph. So you basically increase the clickness of the graph a lot.
A lot of clustering. Is it still random?
It's still random. It's still a Poissonian distribution, degree distribution, with I think it was double average. But it should be more or less the same, but the results are not the same because of this community structure. It is the community structure which is creating the topological traps.
Since your line graph here for one node is completely connected, is that not similar to then making basically you have the node described by a single dynamic variable that you introduce several dimensions, which then incorporate or represent the links?
Several dimensions?
In other words, if you say if you have a bilingual, if you are a person with many languages and you have connections with other people, and relative to the connection, you define the language. If you now say you have each of the language one of your state variables.
So you will have one state variable for each link that you have, no?
Exactly.
One dimension for each.
Is this comparable to this or not? To the line graph?
I don't know. It may be, but then, when you have states on the links, this dimension of this node should coincide with this dimension of this node.
Exactly.
Yeah, if you introduce that, then I think it would be more or less the same.
In the transformation between graph and line graph is one-to-one or always?
There are graphs which if you treat them as line graph, you cannot go to an original. You cannot find an original graph.
Okay.
But from a graph, you can always find a line graph. So, as I say, it is precisely this community structure which, summed with the surface tension of the majority of the normal majority rule, which creates topological traps in the line graph, which become bottlenecks basically, which prevent, for example, if a state wins here, maybe the opposite state wins here. And these, which represent more nodes, cannot invade this because of the bottleneck here. So those are the topological traps which give rise to the frozen configurations and also to the blinker traps. So, okay. Yeah, from here on there is more questions because this is going to be part of article yesterday. Okay, we have seen that when you go from the graph to the line graph, you increase the community structure. And this gives rise to topological traps, which then become frozen coexistence configurations or dynamical coexistence configurations. But now a question is, those disordered configurations, are they robust against perturbations? Are they robust against noise? Because we have seen that we have this kind of bottlenecks. But what if a random perturbation changes the state of this node in the bottleneck? which is the same, changes the state of this precise link. So this is what we are going to study in the form of a temperature. We now define this temperature, which basically is, well, the majority rule is zero temperature Glauber dynamics, as I told you. This dynamics defined for the links, again, we have an Erdős-Renyi network with 10 nodes and average degree mu, or, okay? If S alpha defines the state of link alpha, we can define a Hamiltonian. The normal way is in model, like always. Well, here there's a trick. This normalization J has to take into account that this Hamiltonian has also to be available for use when the network is a fully connected graph, and take into account that this limit must always exist. So from here we define a probability of change, of flipping one link, which is the probability to change state. Again, we have random initial conditions. We choose a random link and compute its probability to change state. Then we generate a random number, and if the random number is less than the probability, again, like always, we change its state and repeat this. This is the normal Glauber dynamics, but basically we define it for states which are on the links. What we find with this, it's very important, this order parameter. You probably know the, how's it called? The density of active links from other models presented here. It's widely used in the Volter model. Active link is a link connecting nodes in different states. That's why it's active, because there are interchange states. Here we have to redefine it to take into account that now we have states on the links, not on the nodes. So in the original graph, this order parameter represents the density of nodal interfaces. A nodal interface is basically a connection through a node between two links. So this is one interface, this is another interface, this is another interface. So you have to count the number of interfaces in different states divided by the total number of connections through a node. But in fact, it is much easier to understand what this order parameter is in the line graph. Because in the line graph, it's the normal density of active links. So here, for example, you have this active link, this active link, this active link. You have another 3 from this node, and another 4 from this node. So basically, then you divide by the total number of links, and you have this. And this is the order parameter because, of course, it's 0 when all of the nodes here have the same state. And it is 0.5 in random, well, 0.5 is the maximum in random conditions. We study this order parameter. Well, here you have the average value of the order parameter, and there different realizations. What we see here is that for zero temperature, of course, the system does not order, as we have seen and as Juan has shown. For small temperatures, we see that the system still does not order. It arrives to some kind of plateau. And when we increase the temperature, like for example this value, the system is able to order. If we go to single realizations, it's much easier to understand. This is the zero temperature case, like Juan showed. You can see that those plateaus are basically runs that arrive to some kind of frozen or dynamically trapped configuration. Some of them are moving here a little bit. Those are the dynamically trapped configurations. When you have a small temperature, so a small level of noise, you can see that even if some of those apparently before frozen configurations are broken, so the dynamical traps are not longer there, so the system orders quite fast, but some of them are features are not able to order the system. So some configurations are robust against slight, small levels of noise. Here what we plot is the average raw. Well, this infinite is not infinite, it's just the final time that I simulated, basically. So it's kind of the stationary state that I find. You see that for small temperatures, this is the important point here, for small temperatures, they are robust against the, well, the configurations are robust, you find them disordered. While if you increase the temperature, here is the order regime, and this is noise regime. Here, what you see is basically just noise. However, we know, I mean, if you look at the system of links with their states, and you imagine a temperature, of course, you know that some of the topological traps may need a lot of random perturbations to be overcome. So, in fact, what happens is not that the system does not order, but that the time to convergence to order is so high that basically maybe you need sometimes the age of universe to find the system ordered. So let's see what happens now with the coevolving link states majority rule. What we introduce now is basically a rewiring mechanism. So we have seen that the community structure gives rise to the frozen coexistence and dynamical traps. We have also seen that some of the topological okay, but what if the perturbations are topological? So what if we introduce a rewiring? Now we forget about temperature, we go back to the original majority rule studied by Juan, and we add a rewiring mechanism. We will have dynamics of link states plus the evolution of the topology, so we have a coevolution model. Coevolution is something that has been studied recently in many social systems, and there are a number of articles, in particular some by Federico, where they study coevolution systems with the water model, for example, and most of them, what they find is a fragmentation transition. No? A fragmentation transition means that depending on the value of the probability of rewiring, so depending on the relative speed of the rewiring process or the dynamical process on the nodes, you find a fragmentation transition. So for one component, while when you increase the probability of rewiring, you normally find that the system breaks into a number of components. It can be 2 components, same size, or it can be many components, it depends. So then a third question is, okay, we will introduce this rewiring, but will the system fragment or not? And if we find a fragmentation transition, what kind of transition, how to characterize it, etc. Again, we have an Erdős-Rényi network with a fixed number of nodes and given a average degree. Again, the states of the links are defined in this way. You have 2 equivalent states, and to the majority rule, we add a rewiring mechanism. This rewiring mechanism is inspired in the case of language dynamics, and I will tell you afterwards how. What we will have is, again, random distribution of initial states of the links. Now, we choose a link. I think it's easier with this example. We choose a link at random. Then, we choose one of the 2 nodes. And this is the node that we will, well, first with probability P, of course, we have rewiring, and with probability 1 minus P, we have the majority rule. No, the majority rule, we already know what is it about. So the rewiring, in which does it consist? It consists in choosing randomly one of the ends, for example, I, and then analyze if I is happy with the state of the link ij. Happy means that it is in the state of the majority of its conversations or not. This is, as I say, inspired in language dynamics. So in this case, you see that I is not happy or not comfortable with the state of this link because it prefers to have all its conversations in the same language, just for, I don't know, to feel more comfortable, whatever. So in this case, I decides to rewire the link to a randomly chosen node. And then you repeat this. In the case of languages, it's clear that when a speaker is uncomfortable with his relationships, he can always just stop this relationship and start a new relationship with other agent in the language that he prefers.
Again, this air-constrained network is just at the beginning. So,
yes.
This property. This is just initial condition. Later, the network will be a different thing.
Will evolve. Yes, yes. You find it always random network with Poissonian distribution, but yeah, it's just initial condition. The orthogonal.
May I just ask why you call this coevolution? I don't see that. I only see link dynamics here. You have also the creation and the removal of link is link dynamics, but there is no node dynamics here, is there?
You are right, there is no node dynamics, there's only link dynamics, but there are two different link dynamics. There is the dynamics of states of the links and the dynamics of the connections of the links.
You add some randomness into the link dynamics, okay. But where's the coevolution?
You add some randomness to
it? On the probability what you link?
No, it's not random. It's not random.
Yeah, but you randomly add some links or remove some links.
And change the state of the links.
Yes.
The second thing.
But it's all about the links. There is no node dynamics. There is no coevolution.
And if you go to the graph line, you change both.
No.
If you go to the line graph, you have states on the nodes which change, and you have links of the. But it's coevolution because you have the two things.
The original concept of coevolution is that we co-evolve, couple the dynamics of the node, of the state of the nodes and the network. Okay. Now you don't have states in the nodes. You have a state in the links, and you are changing in a couple of dynamics the state of the link and the network itself and the topology. But both is link dynamics. You just have two different rules for link dynamics, no? Well, but I don't know what you mean by link dynamics. There are two things that are evolving. The network, and the network itself, the topology, and the state of the links. The state of the links is also part of the topology. No. The state of the link has nothing to do with the topology.
You can say it's there or not. But,
if it's only binary, yes. But having zero state or having no connection is just having a zero weight. That's all.
No, but here it's different. It's not. Here, states are not weights. Are two equivalent states: language A, language B.
Yeah, so it's binary.
Yeah.
But then if non-existing would not be A or B, it would be 1 or 0.
Okay, but here you have a third state.
At least in this way, you have two dynamics on two coupled on two different properties. But Daniel is saying 1 and 0, and what did he say again? This is the coevolution. Not fully understand what you can discuss later.
But I think it's clear that you have two different things which are co-evolving, as Maxi said, the topology, or you can think it in terms of what Ricardo said.
I mean,
if you go to the line graph,
then
you have node states, which you have a dynamic of node states, and you have a rewiring of the network.
Let's continue later.
But I mean, one is knowing a person and talking to it, and the other one is in which language you talk. So it's different. So it's two different properties, no?
Yeah, or this is a property with a mixture.
Orbit 3, the orbit 3 state.
So coming in 101 in the polygon language plus 1 and 0. Which is what we said.
So 1, 0, 1.
In the 1, 0, 1.
Yeah.
Okay, so mapping it to a three states. So let's go to the results with that rewiring that we defined. Again, what we study is the order parameter. Here, we find something quite different from what we saw in the temperature case. Here, we see that the slightest probability of rewiring that we introduce is able to quite fast order the system. If we go to individual realizations, we notice something quite interesting here, which is that some realizations order very, very, very fast, while other realizations stay longer, but still they order on a reasonable time. We will see then that there are like kind of two different time scales for the realizations which order in one component or two components. But this is a second question. So yeah, even slight amounts of rewiring appear to be enough to order the system in reasonable times. But what are those final states? And what are the final configurations that we find? As we saw and in other co-evolving articles, we find a fragmentation transition. So some final configurations are one component, some others are two components, basically. Here, what we plot is the, well, yeah, let's go first to the video. What we see is the histogram of relative sizes. Relative sizes is the proportion of the network which forms part of the largest network component. So when you see in the beginning, when we start from zero probability of rewiring, all realizations end up in one component. In fact, they do not order. But very soon, you see that more and more realizations break. The realizations which end up in, well, in this area here with relative sizes of 1/2 of the system, that means that the system breaks up into equal-sized components. Here you also see a small point because sometimes you find one node or a couple of nodes which are apart from the rest, but basically we always find two more or less equal-sized components. That you can also notice it here, where we have a color map of, again, the distribution of relative sizes, but in this time of the largest network component. So those distributions here would be the ones ending up in one component, while the rest of them fragment. As you see, when we increase the probability of rewiring, first we have an initial phase where more or less any system size can be found, and very soon the system starts to break up into equal-sized components. But in this area you can find whatever distribution of sizes. Here we plot the fraction of runs ending up in one component, which gives an idea of the fragmentation, a very clear idea of the fragmentation transition. You have in this point, the first point, probability of rewiring 0 is the disordered point. Then you have a region of bistability, which means that more or less you can find the system or in one component or in two components. Both solutions are available. And then you have a region of fragmentation, where you always find the system broken in two equal-sized components. This allows us to define for each system size P star, which would be the last probability for which we are able to find one component solution. And with this P star basically defines the end of the bistability region. The bistability region would be between 0 and P star. We can rescale this, rescaling the x-axis, the probability of rewiring. We find that we can collapse all the curves into one with a given exponent of the system size. This, what it means is that the power law behavior of the rescaling factor, what it means is that the bistability region disappears in the thermodynamic limit. So all the curves, when you increase system size, they tend to approach the y-axis. So in the thermodynamic limit, there is no bistability region. So technically, there is no phase transition. A typical way of defining a transition point is the maximums of the size fluctuations. So the relative size that we saw before this graph, but instead of doing it for the largest network component, you do it for all components. What we find is this kind of curves Again, what you see with increasing system size is that they become thinner and thinner, and their height increase a little bit, but very slowly. Again, here, the power law behavior points at the fact that the stability region disappears and the transition disappears in the thermodynamic limit. So we find a fragmentation transition, but quite different from the ones presented in the literature before, which is not, R1 is, technically speaking, not a phase transition. When we study the time evolution of the system, the most interesting thing that we find is that we find these two time scales that you see here. So if we plot the survival probability, so the probability that the system is still, well, active, like things are changing, for small probability of rewiring, we can see clearly the two time scales. This ordering process would be due to the runs which order in one component, while this ordering here is due to the runs that fragment. So we see that the runs which order by majority rule and just slight just slight rewiring order very fast, while there are some realizations which are not able to order fast, and they are broken into components. And this process takes longer than the first one. One can, from there, increase and increase the probability of rewiring, and what one sees is that the ordering times decrease, so the ordering process is faster and faster, but the one which decreases faster is the fragmentation process. So the rewiring is each time more easier for it to order the system. One from here can try a mean-field approach based precisely in these two time scales, in these two ordering processes. So here in the graphs of rho that I showed you at the beginning, one can notice a first very fast ordering process because the rho starts at 0.5, always, because we start from random initial conditions. There is a very fast ordering process and then a slow ordering process to break up into components, for example, in those cases. So from here, we can suppose that we start from two components. One has a consensus to one state, the other one has a consensus to the second state, and they are connected by frozen and dynamical traps. So this kind of bottlenecks. This link would be a frozen one because it has the same number of neighbors in the same number of neighbors in one state and in the other. This link would be, this one will be a blinker link. This one will be a frozen one because it has more neighbors in this state than in the other. So from here, we can try to guess that, what we do is we study the dynamics of these links, and from the dynamics of these links, we are going to find dynamics of rho, basically. So the density of bottleneck link, we call it beta. Then in a single time step, let's say that a bottleneck link is chosen with probability beta, because beta is their density. Then with probability p over 2, the node of the bottleneck, which is uncomfortable with the state of the given conversation, is chosen, so a rewiring takes place. When this rewiring takes place with probability 1/2, you rewire to your own component, so you create order, and the change in beta in that case would be -2 over mu n. So then you can also relate this average number of, the average number of bottlenecks with the average number of. You can find an equation for the evolution of rho. well, first you find an equation for the evolution of the density of bottleneck links, and then you find an equation for the evolution of rho, which tells that it varies in this way. So it's an exponential decay. We check this exponential decay, we fit it, and we see that this mean field approach works mostly quite well, even if it does better job for large P than for small p. This is an example, well, with different system sizes and different average degrees. Then one can also assume that the system breaks when the number of bottleneck links goes below the change of, well, below one bottleneck, basically. From here, one can find an expression for the ordering time of the fragmentation, and we see that the fitting also works quite well. Here we represent the order do not fragment. So then, as conclusions, we have studied the robustness of the frozen and dynamically trapped configurations that were defined before in this work by Juan with majority rule link dynamics. Some of these disordered configurations appear to be quite robust under stochastic perturbations, even if in theory the system orders in the end, the time needed to arrive to disordered state is so large that in practice one can say that they stay disordered. Topological perturbations seem to be quite more efficient in ordering the system, in breaking up those topological traps. So even slight amounts of rewiring are able to whether order the system in one component or break it into two components, but always into absorbing configurations. And the coevolution of the network topology gives rise to a fragmentation transition, which has been characterized and appears to be somehow different or quite different from the ones studied in other coevolution models. Now, just as a short outlook of what before, he was saying that there is no coevolution because everything is related to links. So what we are adding now is states on the nodes too. So we said at the beginning that the language is a property of the relationship between two speakers. But there are also some properties of the speakers which can be relevant for the process. So for example, the knowledge of a language is a property of the speaker. The preference for a given language is also a property of the nodes, of the speakers. And in particular, we are going to focus on this preference, or we are planning to, because this is mostly work not in progress, but it will be work in progress. So we have been making up a connection between nodes and links if the node state is preference. So how nodes affect links? One can say that NJ agents with high preference for a given language tend to impose it in all their conversations. How one makes the connection from links to nodes? One can say that contact with a given language increases the agent's ability to use that language and its preference for it. So one can couple the evolution of node states and link states. For link dynamics, what we have been thinking about is, well, basically defining a variable for the nodes, for the state of the nodes, which would be the level of preference for language A, say. This would have discrete states related to the number of links. Then one can, from the states of two nodes connected by a link, one can define a preference for the link. So one has preference for the nodes, and the preference of the nodes establish is a possibility. Because defining it in this way, extremis nodes, so nodes with preference 0 or 1, directly impose the language the conversation, in the given conversation. Then one defined a social pressure for language A on link ij as the fraction of links neighbor in link ij which are in state A. This is more or less what the majority rule does. So the equivalence from this to the majority rule is saying that the preference of every node is 0.5. If you put 0.5 in every node, you recover the majority rule that we have been studying so far. So then you have like a competition between the majority rule and the preferences of the nodes. A link changes its state when the social pressure overcomes the link preference of the particular link that we are updating. So it's like a competition between the majority rule and the preferences of the nodes, and the preferences of the nodes basically establish a threshold from which the majority rule always overcomes the result of the preferences. Then the node dynamics, one can define, once you have the discrete states, when a node is updated, its state goes up or down in this discrete set according to a certain probabilities. We have been thinking of those probabilities because in this case, you go up when you have more interactions in that particular language A. And we introduce this plasticity or relative speed of both processes. So next questions to answer with this is basically, do we have coexistence? Do we have coexistence states of both languages, or do we have extinction? The typical question. One can ask one question quite interesting here, what's the role of extremists? So what's the role of people inside the network who have preference 0 for one language, or preference 1, so the ones who impose the language always? And also a third relevant question is if we find different behaviors depending on the relative speed of both processes. So this epsilon would be a little bit equivalent of the probability of rewiring in the previous examples. So thanks for your attention, and questions, comments.
Okay, further questions?
One short question, maybe you know about the project in Potsdam Institute. This is called COPAN project. They actually study this coevolution of the networks in society and also climate networks together. And what people, for example, studying climate networks study, they fix, for example, the density in network, and they study the dynamics of the climate network, because basically sometimes climate has some properties, they can be studied through these climate networks. And the question is, how do you think, for example, using this line graph, is it good to use line graph, for example, for complicated structures, complicated climate networks with fixed link density? So you fix, for example, number of your links in the graph, and you describe line graph by line graph, basically the dynamics of climate networks, for example. I mean, it's just the question. Can it be useful if these climate networks are very large, for example? Like,
but do they use states of the links also, like properties of the links? Or?
It can be, yes, they can use, for example, the value of the correlations between variabilities of the temperature or something. So they can use rates, yes. But I mean, the question is when using this line graph is relevant, because sometimes maybe you don't need it. Because in your case, yes, you demonstrate it. It's maybe you need it. But in, for example, for large systems, is relevant, or?
In some cases, it can be just going from graph to line graph can give you like qualitative understanding of what's happening. Like here, when we used the line graph to understand the bottlenecks and so on. In other cases, it may not be that relevant. But you always have to take into account that if the dynamics is on the links, you always have this change of topology.
Very nice talk. I have one question. I'm not sure whether I misunderstood or not, but you spoke about social pressure in the end, and that implies in a way a hierarchization of link states, right? Or of basically the links that you consider in a network. And as far as I've understood it, the links you update, via your update rule, no matter if you're applying a majority rule or whatnot, is chosen randomly. But if you have an extended large network, shouldn't then the links be preferred to be updated in general that are basically under kind of strain or kind of a pressure from the network? Or do you actually do that? Maybe I misunderstood that.
No, here you update links. I mean, you randomly choose a link to update. But I don't know what you mean with like choosing preferentially some links.
Yeah.
And not the others.
What do you mean a weighted link?
Not weight link, but an update link weight basically, or link update weight, so to speak. So I mean, if you assume you have a group of people and everyone gets along pretty well, just two subgroups, maybe not so much, then maybe you should choose that link before the others because there's more strain in the.
So so giving more weight to some of your contacts than to the others, you mean?
Yeah.
Yes.
Yeah.
No, I think that what he means is that not all links are updated at the same rate, but the rate of update of the links which are under pressure should be faster.
Okay.
Yeah.
Which makes sense.
Okay. That makes sense. Well, we haven't thought about that, but it makes sense.
Regarding the last transparency, when you comment on this extremist,
Sorry?
but you comment on the role of the extremist. An extremist is somehow monolingual.
Yeah.
Monolingual is that one that no matter what happens will not change the language because doesn't know any other. And the extremist doesn't matter, doesn't know, is not going to change the language because doesn't want. The practical in the network is not whether he knows or wants, it's whether he changes or not. So the question is there a difference between extremists and monolinguals? And if there is not such a major difference, you might answer that. You might already have an answer for that question by looking at what is the role of the monolinguals in the present model.
Yeah. Regarding the difference between monolinguals and extremists, let's say that here, at a given point in time, you can have an agent speaking one language, but his preference can be not 1 or 0.
Yeah.
So he doesn't need to be an extremist.
Correct,
but with time, it's probably that since the dynamic says that you increase and increase and increase, so in the end.
Or even if the dynamic doesn't say that, but if it is real an extremist, it's like being a monolingual.
Yeah, if you are extremist, you are monolingual, that's for sure.
So then the role of the extremist is the same as the role of the monolingual.
I'm not sure. You can be monolingual, but not extremist. But you cannot be extremist and not monolingual.
I mean, if you are monolingual and you are not extremist, how you are going to talk with another language which is not the one that you know?
No. But you
assume
assume
this is the one that no matter who is the other one in the link is going to use a single language.
Here you assume that everybody knows both languages. Implicitly assume. Because except in the case where you are in 0 or 1, you can always have some conversation or change one conversation to the other language. So
yeah, but the extremist then a suggestion is in all these things that you put there, I don't know if you are putting a mechanism for creating new links. In the sense that from time to time you may encounter another person because you are meeting them, I don't know, you find that you have to meet someplace and you have to talk with, and this creates a new link, and this is something that also is going to happen in the society. So there should be a mechanism for creating links randomly among people which have no connection. Should be independent, or they should be at least to a large extent should be independent of the fact that whether they do speak the same language or not, or if they have a preference. They might just encounter and be forced to interact.
Yeah, but step by step. On the average, the number of links should be concerned. So you cannot go on adding links and links, because step by step, this is a fixed network. This is a fixed network. It is obvious that the next step is that the network also evolves in time.
If I mention the law of coevolution, will be not the first time this afternoon.
No.
So what? Again, that the law of coevolution creates a new network.
Well, I can tell you possible models 3 steps beyond in complicating it.
But this is a well-posed question. I mean, you have a link to just establish it for. You do not expect it, and you have to contemplate that possibility of, because that will generate new links on possible stationary states and will make this consensus of.
It is the same old story that the Beatles would say. When you give a talk in physics, people accept that you first study the most simplest case. And people in the audience would never say, well, but you should take into account that possibly this system is in contact with whatever that will all thing happen. And that's what you are saying. Okay, that's next step.
Let's go to the next question.
I don't agree.
You talked about probabilistic rewiring. Has anybody studied Hamiltonian rewiring?
Hamiltonian rewiring?
Just purely deterministic. I mean, you choose with
like
given probability
but you
a link and then randomly choose one of the nodes.
Yeah.
But
what you mean is the direction of your rewiring. To do it to a determined one, you mean? Or
for example, extremist looking for extremists.
Yeah, for example, extremist of the opposite one, you mean?
If it can be an IC model, you can always choose some terms in the Hamiltonian to do that.
I don't know if it's been studied, but it makes sense to. But in this case, I mean, the rewiring mechanism that I studied, it's random in the sense that when you rewire to a randomly chosen node. But it makes sense to rewire to a node who has most of its conversation in the language that you prefer. That makes sense. And in other rewirings, like in the motor model or so, you normally, as far as I know, you normally rewire to a node which is in your same state. So this is kind of direct. I don't know if it's exactly what, but
he will like something like in the Glauber dynamics and stochastic dynamics, but at zero temperature is deterministic. You jump in a given direction given by your neighborhood. It's a fixed word. Probably what Fernando is saying is that, okay, because there is a rule with the link dynamics, and you look at your neighborhood, and then given your neighborhood, there is a fixed rule what to do. It would be interesting for me. Well,
the one that has more similar neighbors than me or something.
Yeah, that could be. Or looking to new neighbors through my neighbors, this type of thing.
One more question concerning the rewiring. So your motivation I think, was that you have some agent in the network who's maybe unhappy with the link states he's got, and then with probability P rewires the link, one of the links, and 1 minus P majority rule and so on, right?
Mm-hmm.
But that doesn't include for any other possibility. For example, not to rewire, but to switch off the link, right? So basically break off the social contact and maybe not talk for a new friend.
That's always a possibility. Also, what you could do is break this link and start a new link between two random nodes, so not keeping this conversation. I mean, in order to do what you say, but at the same time keep the number of links constant. It's an idea. One could define it differently.
side note, there's people who have studied in a regular lattice in three dimensions, when you co-evolve the state of the node and the state of the links, and the links can have +1, 0, or -1, you recover at low temperature or 2 electrodynamics. That probably doesn't have anything to do
Comments? We thank Adrián for the talk.